So we are ready, fortunately, to start the presentation.
Yes,
the name of the presentation is on liquefaction mitigation, and in particular, I would like to share with you what are the findings that we have found on the potential of nanomaterials. In particular, I'm going to present a specific nanomaterial which is called Labonite. Okay, so if I were to summarize this presentation, I would like you to take 3 ideas to home about this presentation. The first one is that this was the first study that was made with Labonite on earthquake engineering, that we are going to provide evidence that it's possible to engineer and manipulate the mechanical response of granular matter. In this case, the granular matter that we are dealing with is sand. And also, probably the most beautiful one is the fact that we show in this study that there is an intrinsic correlation between the nano world, the micro world of sands, right, and large strain phenomena like liquefaction. Okay, so the overview, what we are going to do, we are going to talk about the vision, the scope, the experimental approach, the research highlights, and I'm going to end with some contributions and challenges that we have faced lately, in particularly on this topic. So let's start with the vision. What is our vision? We want to do engineering across scales. We want to work with a fluid, and we want to manipulate that fluid. We want to engineer that fluid with an innovative material. And in this case, that innovative material is the nanomaterial called Labonite. Okay, what we mean when we say, okay, we want to do engineering across scales. We want to work with a nanomaterial. That means of the order of 10 to the minus 9 meters, right? We want to apply it into sands. Sands are in the order of 10 to the minus 6 meters. For what? To study a phenomena that when it happens, it expresses in several meters. That's what we mean when we want to go in across scales in this research. So from very small, we want to manipulate something very small, right, to observe positive effects at very large scales. So when we talk about pore fluid engineering, this we see every day in our lives. We see it in the kitchen, we see it on the streets, we see it on the lab, we see it everywhere. You can see a dessert, you can see concrete, you can see chocolate, you can see a fluid solution. Everything can be, right, can be a granular material with a fluid. It doesn't matter how the fluid is managed. The important thing is that you can always manage the fluid with the granular matter. And that's what we are looking for, particularly in this presentation. Okay, so let's talk about the innovative material. It's Labonite. What is it so interesting about Labonite? The fact that Labonite is very small. In nature, we have that the smallest particle that we have is bentonite, right? It's approximately 200, 300 nanometers, right? With a plasticity index of about 500, 650, right? And that's the smallest particle that you can find in nature, a natural particle. However, we want to work with Labonite. And what are the features of Labonite? Labonite is extremely small. It's 25 nanometers, 10 times smaller than bentonite, okay? That means that it has a higher specific surface area in general, which means that Labonite likes water even more than bentonite does. And a reflection of that is the plasticity index of Labonite. The plasticity index of this material is approximately 1,000 and 1,200, if you will. Okay, and that has a huge implication because you can develop unique rheological properties of Labonite dispersions. That means that you can engineer solutions of Labonite to achieve a certain result depending on what you want to, what effect you want to induce. Okay. Also very important, Labonite, as we said, right? Bentonite is natural, Labonite is synthetic, right? So that it means that it's manufactured in the industry. Okay, so what are the scopes and objectives? We want to explore the use of Labonite.
Felipe, sorry to interrupt you.
Yes.
Can you just hide your bar that is there?
Ah, okay. There you go.
Yeah, thank you.
Thank you very much. So what is the scope? We want to explore the use of Labonite in geotechnical engineering and how we want to achieve that. We want to understand the influence on the cyclic behavior of sands. We want to examine the extreme effects of plasticity, right? The plasticity of Labonite is huge, 1,200. And we want to expand the experience gained from previous work that our group back at Purdue, we did in, or mainly Chadi did, right, on bentonite. That's the right thing to say. Previous to this work, there was a work made with bentonite, led by Chadi El-Motar, who happens to be a professor in University of Texas, Austin. So he developed a lot of knowledge, right? And particularly my work focused on improving, right? Going further with a new material. And in that case, provided bentonite was the smallest natural material, we went to a synthetic material that it's even smaller. So what was our experimental approach? We did laboratory tests to address the small and large strain response. We worked with a very well characterized reference material, which is Ottawa sand. You can find many studies in the literature about Ottawa sand. And we wanted to work with really small quantities of material, of this case, Labonite, of course. And in the work of bentonite, the amounts of material used was approximately 3, 5, and 10%. We wanted to go even smaller than that. So we went with only 1 and 3%. And also we did some experiments with 5, but we focused on 1 and 3, okay? And we used the Labonite just as we received it from the industry, okay? So we received the box from the manufacturer and we worked with that material. So what are the main tests that we did? We did triaxial. Why? Because with triaxial, we can study the large strain phenomena, right? The cyclic behavior when liquefaction happens. We did resonant columns. Why we did resonant columns? Because resonant columns allows you to measure and study the behavior of the properties of the soil at very small strain, 10 to the minus 4, 10 to the minus 5% to up to 10 to the minus 2. If you have a very good equipment, you can get to 10 to the minus 1%. Okay, but so we want to do a full overview of all the strain ranges that we observe in geotechnical engineering. So strictly speaking, we are going from 10 to the minus 4 to up to 5% of deformation. And what we did to complement those observations, experimental observations, we did imaging. We did imaging with laboratory microscope and also with SEM, which is a super good microscope, if you will. So why we addressed in particularly the SEM? Because SEM allowed us to see the effect at granular level of what happens with the material selected, which was sand, right? Is sand the ones that is going to suffer liquefaction, and how it's produced the interaction between the sand and the nanomaterial Laponite. Okay, so we wanted to address that at the micro scale, not only by measuring what's going on in the behavior and the properties, but also we wanted to understand what was going on from the morphological perspective of the grain. What is happening to the grain? So the research highlights, which are they? The first one is that the excess pore pressure and liquefaction resistance must be addressed. So we are going to show the main results on that regard: excess pore pressure and liquefaction resistance. The second one will be the insights from the small strain behavior that will allow us to understand the first one, right? And the third one is that we want to study the fabric and the controlling mechanisms. So with the third highlight, we can explain the second, and with the second, we can explain the first, right? So let's see what were the main observations that we had. The excess pore pressure. When we observe the excess pore pressures, we see that this is a plot of liquefaction, right? With the main liquefaction issues that you observe when you do a cyclic triaxial test. And you see the deviatoric stress, right, on the upper left. And you see a sinusoidal stress reversal, right? If you see on the right, in the upper right, what you observe is that although you are applying a significant shear, right, you don't see much deformation. You start to see deformation only at very large number of cycles, right? This was a cyclic test that withstood approximately 110, 120 cycles. But you see that for over 110, 105 cycles, there were no deformations. However, there were excess pore pressures, right? And you can see on the lower right, what you observe are the stress path, right? So these are the typical plots that you observe when you do a cyclic triaxial test in conditions to a sand, okay? So what would happen if we apply Laponite? What we observe is that when you apply Laponite, you observe that the material affects all the stages of excess pore pressure generation. You can see here a test in similar conditions, right? But for Laponite, meaning that you have sand with the nanomaterial included, right? You have a specimen that you prepared with Laponite and sand, okay? The material of Laponite is in very small quantities. Remember, it's only 1 to 3%. However, you see a significant decrease in the number of cycles, okay? And what is it that you observe? You observe here is the excess pore pressure, and you also observe the mean excess pore pressure, right? Because we would like to understand what happens with the excess pore pressure when you cyclic these in undrained conditions, and how you can characterize that. You can have, if you observe here, in this portion, you have, in the mean pore pressure, you have a straight line, right? So you can set a slope. What you observe also is that here you have the excess pore pressures and here you have the strains. When you observe the strains, you don't see, you see almost zero strain, right? However, you have excess pore pressure development. But you observe that when the strains start to get large, right, you observe that the excess pore pressure is significantly developed, right? The deformations, when you have a sand, the deformations starts when you have an excess pore pressure significant in the material. So based on these two observations, what happens when we apply Labonite? What we observe is that the slope is decreased with respect to clean sand. That means that when we have a sand with Labonite and we apply cyclic stress, right, resembling an earthquake, we observe that this slope has a smaller value with respect to clean sand. That means that when you have a specimen with Labonite into your sand, what you have is that the excess pore pressure is developed, but is developed at a slower rate, right? And that's very important because that's a sign that liquefaction, probably we are not going to prevent liquefaction to happen, but we are gonna delay it. And that, in practical terms, means that you are preventing liquefaction, right? Because if you are having liquefaction in, let's say, a number, 20 cycles, right? An earthquake, 7.5, 20 cycles, right? With Labonite, probably you are gonna liquefy, but you are gonna liquefy with 100 or 200 cycles, right? One order of magnitude, at least, we're gonna see that. So that means that in practical terms, okay, it's gonna liquefy, but for what we need from a prevention perspective, it's working okay, meaning that effectively Labonite is mitigating liquefaction. When we observe the deformations, what we observe here is that the numbers of cycles that you need to trigger liquefaction, right, or to trigger, or better, to trigger deformations is significantly higher with respect to clean sand, meaning that another sign that we are effectively mitigating liquefaction. Okay, when we observe what happened with the excess pore pressure at the time that the deformations are triggered, we observe that that value is significantly increasing with respect to clean sand, right? And that's another sign that we are significantly decreasing the excess pore pressures with Labonite. When we observe the liquefaction resistance, which is the measure that we use for design, we observe that with respect to clean sand, the addition of Labonite makes a huge difference, and that the liquefaction resistance is effectively mitigated by the presence of this nanomaterial. You can see it in this plot. Okay, and what we plot here in the last portion, we plot a very interesting parameter which we called the grace period. That's how we called it, the grace period. The grace period meaning the difference between the point at which the large deformations start to which the excess pore pressure reaches 100% of development. And what we observe here is that that portion here, see, which is pretty much this portion. And leak here, 100% of excess pore pressure, right? And trig, right? The moment when the deformations start. We observe that that quantity and leak minus and trig is significantly increased when our specimen of sand has Labonite in it. Okay, that's very important. However, that was not the only observation, and this observation in particular, and that's why it's isolated in this slide. The observation was much more than that. We went to the first quarter of the first cycle of loading, which is pretty much a monotonic load in a very rapid way. And what we observe is that Laponite affects the response from the first cycle, right? Meaning that Laponite affects also, or could affect, the monotonic response of the sand, meaning that we should study also the monotonic response. And that's what we have been doing lately. When compared with respect to other materials like bentonite, we were very familiar to bentonite, right? So when we compared the behavior of a sand with bentonite and a sand with laponite, we observe that laponite, right, which is the orange dots here, the orange dots here, they are the laponite, compared very well with higher amounts of bentonite, meaning that we are using a synthetic material, we are using less quantities, we are investing less time, and we are having similar improvements. So from that perspective, Laponite optimizes, right, the liquefaction mitigation of this sand, this particular sand that we are studying. So that was large strain behavior. Do you consider that in the beginning we said, okay, we're going to go across scales, right? We are going from very small to very large. But the way we approached the research was to do at first the large part, right? The large strain part, because we wanted to see if effectively the material mitigates liquefaction. And check, it's done. Laponite mitigates liquefaction. So now we want to understand why liquefaction is mitigated. And for that, what we need to do is that we need to go to the small scale, meaning that we need to go to very small strains, 10 to the minus 5, 10 to the minus 4, that order of magnitude. So for that, right, if we want to get insights from a small strain behavior, what we need to do is that we need to work with the resonant column. And here what you observe in this plot are the degradation curves of clean sand in white and sand with laponite, only 1% of laponite in orange. And what we observe here is that you observe the normalized shear modulus, right? This is a very important curve for design, the normalized shear modulus. And here what we observe is the normalized pore pressure, delta U over sigma 0 naught, okay, which is the initial confinement. So pretty much delta U over sigma 0 naught, sigma prime naught, sorry. That means is the percentage of excess pore pressure that you develop during this shearing, right, at very small, in the very small strain range. So what is it that we observe? What we observe is that the shear modulus degradation, the normalized shear modulus degradation of sand and sand with laponite are very similar in the very small strain range here, in this range. However, when we reach the formations of 7, 6 times 10 to the minus 3%, what we observe is that we start to observe a divergence between the degradations of clean sand and sand with laponite. While clean sand degrades at this rate here, that we are showing here with my cursor, right? What we observe is that when you have laponite in the sand matrix, what you have is an extension with respect to the clean sand, meaning that laponite is stiffening the soil with respect to clean sand. there is something happening in the particle, at the particle level, that somehow the sand is getting stiffer, right? With Laponite with respect to its clean state. And that's very interesting. That's very interesting. So we observe an improvement in the degradation, right? When you have Laponite, Laponite helps you to withstand better the cyclic shearing. If we observe the excess pore pressure, what we observe is that the excess pore pressures in clean sand develop really fast, right? However, when we have that same sand with the nanomaterial Laponite, what we observe is that the excess pore pressures are delayed. And this is an observation made in the low strain, right, in the low strain regime, that helps us to explain what's happening at large strains, right? They go along. They start to show us, right, that there is something important happening at the particle level, right? But this was not the only observation that we have, right? We observe that when we compare the behavior of sand and Laponite at 1%, and we compare it with sand with bentonite at 3% and 5%, the behaviors are quite similar, okay? Only when sand with bentonite is approximately 5%, there is a more significant difference, right? Sand with bentonite at 5% is in the upper bound of this degradation. However, if we were to have sand with Laponite at 5%, we would be even higher, okay? However, this was the most intriguing observations that we had when we did this study. This is a study 5 years ago. And what is it that we observe? We observe, look at this. When we have sand with Laponite at 3%, we are in this line, right? This is the normalized shear modulus with respect to the normalized confinement, which is another very important chart for the design of geostructures, okay? Because it's very important to understand the effect of confinement on the shear modulus, right? So when we have 3%, we are below clean sand. However, when we have only 1%, we are over clean sand. Isn't that strange? That is very interesting from a particle behavior perspective. When we have clean sand, we have a shear modulus. If we have 1%, the shear modulus is higher. Our intuition would say, okay, if we were to have 3%, the shear modulus will increase even more, because that would go along with the observation from liquefaction studies, right? From the large strain phenomena. However, we observe that when we have sand with Laponite at 3%, the shear modulus is below even clean sand. Again, there is something happening at particle level. So when we explicit this, right, and we want to understand what is going on, and we evaluate it from a different perspective, and we observe the normalized shear modulus with the Laponite content, we observe that effectively is like that. When we have clean sand, we have here the white dots. The white dots show us, right, that with confinement, there is an increase in the shear modulus, which is absolutely expectable. That's our expectation always. When we have only 1% of Laponite, what we observe is that the shear modulus increases with respect to the clean sand. However, when we have 3%, the shear modulus decreases with respect to 1%, right? So what is going on? That's when we say, okay, there is something going on at the particle level. There is something that we need to study. So what is it? We are going to study the particle. We are going to get deep into the particle. It's not only that we are going to study the matrix. No. Now we already studied the matrix. We studied the matrix of sand with Laponite. We observe the results that we have at the low strain behavior and at higher strain, larger strain behavior. And although they go along in terms of result, liquefaction is mitigated, dynamic properties are improved. When we have 3%, dynamic properties are not improved. All the opposite, are decreased. However, liquefaction is increased. So what's going on? We enter to the particle. And what you see here on the left is a particle of sand. When you do, and this was made with SEM. When you have this particle of sand and you do a zoom into its surface, what you observe here is that you observe that the surface of a particle of sand is very similar to what we observe when we have when we do a zoom on the moon, right? We observe that the particle of sand has valleys, has mountain ranges, it has a topography, right, at the surface. And when we do another zoom, what we observe here is a basin, right? We observe here a basin. And look at the size of this basin. It's only 5 micrometers, right? 5 micrometers, 5 times 10 to the minus 6 meters. Laponite is 25 times 10 to the minus 9. It's a nanoparticle, right? So let's see what's going on with Laponite. The Laponite powder, when we see the Laponite powder here that we received from the manufacturer, we observe that Laponite particles are like this, right? And when we go to the scale of 20 micrometers, Laponite particles look like this. However, if we go deeper into the particle of Laponite, what we observe is that you see this flaky structure, right? You see flakes of Laponite that could reach a very small size. Here we are at the level of 4 microns, right? 4 microns, right? Here we have 5 microns. So what is our observation? Laponite could easily fit into this basin, and that's very interesting. When we study the Laponite aggregate, right, what we are doing here, we are having a microscope. And with a microscope, we get a microscope, we isolate a particle of Laponite that has been sent from the manufacturer, and we smash it with a pin, right? And we do this experiment at the microscale, right? We do it with a microscope. And what is it that we observe? That effectively this flaky structure of Laponite is completely deformable, completely destroyable, if you will. So Laponite could easily fit into these basins that we were observing here in the surface of sand. So what is it that we are observing? When we have clean sand, we have this structure. This is a fabric of sand, clean sand, right? Relative density of approximately 40%. And here is a structure of Laponite with sand, with Laponite being only 1% of the sand structure. So when we are on the clean sand specimen, what we observe that we have particle-to-particle contacts, and they develop very well. You can observe change forces, right? If you do an image processing, you can see change forces, right, with the application of load. So you have a load-bearing skeleton. However, when you have Labonite aggregates in between the sand particles, you can observe that the Labonite particles are on and in the sand grain contacts, meaning Labonite is getting into the sand particles, and also Labonite is entering the asperities of the sand surface. So we cannot say, as it happens many times with silts, for instance, non-plastic silts in particular, that we observe in tailings. Here in Chile, tailings are tailings for us are very important structures. We're a mining country, so we need to host the tailings the best way we can, right? But and tailings are silty sands, right? When you observe silty sands, depending on the amount of silty sand that you or of silts that you have, you see you can observe that the silts fit in the void space between particles. However, here, although we have only 1% of Labonite is not going fully into the void space. And why that happens? Because of interaction forces. Interaction forces at the particle level, meaning van der Waals, meaning electrostatic forces, meaning little humidity that might exist at the specimen, at the micro level of the specimen, right? So it's not fully hosted in the pore space. Also, here is what I want to show you. There is a strong affinity between sand and Labonite. This is a very nice image. Why? Because we repeated the experiment. We took another pin, and what we did is that to that pin we glued a particle of sand, and then we brought this particle of sand with the pin and we put it in a bed of Labonite. And as you can see, when we have the pin with the sand, right, the sand attracts Labonite, meaning when Labonite gets in contact with the sand, right, the sand can, or better said, Labonite sticks to the sand particle. Okay, and that's very interesting because it's a proof that there is an interaction, right, an attractive interaction between sand particles and this material of Labonite. But that was not only observation. When we change the bed of this particle, right, and we put the particle in a bed of sand, what we observe is that when the sand particle has Labonite on it, and you get it close to another sand particle, the sand particle with Labonite is able to lift another sand particle, and that's very rare. You don't see another sand particle lifting another sand particle unless there is some sort of cementation, right? But with only a little bit of Labonite, we are inducing that effect. So it's sufficient to lift another particle. When the water enters, right, because these experiments are made with water and they are made in under conditions, the situation changes completely. Why? Because now the Labonite and the water makes a pore fluid, right? And that pore fluid has rheologic properties, meaning that the viscosity changes with time. The viscosity changing with time means that the shear strength of the fluid start to, or better said, that the fluid can have shear strength, okay? So when we have Labonite and sand grains, you can see the interaction of the pore fluid. You can see the interaction of the pore fluid with the particle. In this part that I am remarking here with my mouse, right? You can see the sand particle, and you can see here the Labonite fluid, and you can see this structure. You can observe this structure. right? It's like a lattice. And when we observe into another grain, we observe sand grains again, we observe Laponite fluid, and we observe also these pockets, right? Pockets that could be filled with water, could be filled with air, right? It's a very interesting observation. This in particular, this was an observation made by Alain, a good friend of mine, who did a previous work in 2011, okay, or 2012, on the interaction of Laponite with sand. So far, from all the observations that we have done, large strain to study liquefaction, a small strain to address dynamic properties and degradation, and from the observation of the fabric at the particle level, what we observe is that mainly the behavior of sand with these nanomaterials are controlled mainly by two mechanisms. The first one, right, is that there is a particle bridging, right? Laponite acts as a bridge between two sand particles. It can have that effect, right? However, there is a second, that's the next one. And how we observe that evidence of particle bonding and bridging? What we did is that every time after we did an experiment of sand with Laponite, what we did is that we took again observations at the microscope. And what is it that we observed? That we observed that in between the sand grains, we observe these particles of, not particles, but evidence of bridging between the sand particles, right? Due to the effect of Laponite. You can see it here, you can see it here, you can see it there, there, right? So post-mortem, there is post-mortem evidence of Laponite adhesion, right, in between the sand grains. The second mechanism is due to the solid-like pore fluid that is developed due to the interaction of Laponite with water. And we observe that Laponite forms in the matrix of sand, it forms this lattice structure, right, that you observe here with a very well-defined network, crystal network, if you will, of Laponite solid-like gel. Okay, so two mechanisms control the behavior. When you have only 1% of Laponite, what you observe is that the addition and particle bridging are the main mechanisms explaining the observations, particularly those at a small and large strain, right? When controlling behavior with 1% of Laponite, right? You observe it here. With 1% of Laponite, you have an increase of the shear modulus. And why that happens? Because Laponite enters the contact, right? You have the two contacts, the two sand particles, and you have Laponite in between. And the Laponite is deformable. So what is it that happened? When you have the load, the two particles of sand get closer, right, due to the loading, and you have the Laponite in between. And because the Laponite is deformable, the contact area increases. And that means that the shear wave is easier for the shear wave to go through the two particles. So you have a stiffer structure, right? When you have 3%, because of the overflow of Laponite at the contacts, right? What you have is that you have a more unstable material. So you can still prevent liquefaction, but the mechanism is different. The mechanisms to prevent liquefaction are different from when the sand Laponite has 3%. Okay, so the second mechanism is the gel pore fluid of solid-like response that is evident when the behavior is controlled, particularly when we have 3% of Laponite. You also can see the effect on the excess pore pressure generation, right? There is a significant influence of the presence of Laponite on the excess per pressure generation, as we saw in the beginning, right? And here is even more evidence if we compare them and we put them in the context of the ALVA, right? Something is happening to the material. It's not fully a sand, but it's not a sand with, it's not a sand with how to say it, with fines, right? It's a hybrid. It's a hybrid material, right? Due to the interaction of water, sand, and laponite. Okay. So there you can see the observation right here in white. As you can see here in white, is the typical behavior that you observe in clean sands, right? Regardless if the clean sand has or does or doesn't have silty content, right? And here in red, right, red and orange are the excess per pressure generations due to 1% and 3% laponite. So there is somehow we are changing the fundamental behavior of the soil with this nanomaterial, right? So what are the research highlights? The presence of laponite, when we have only 1%, reduces sand particle mobility. If you reduce sand particle mobility, you reduce excess per pressure generation. Then you increase liquefaction resistance and you extend the threshold shear strain, right? The threshold shear strain for excess per pressure generation, and you stiffen the sand structure only with 1% of laponite. The main mechanisms are pore fluid, adhesion and particle bridging, and the mechanisms coexist with one overruling another depending on the amount of laponite. So what were the main contributions of this work? That this work was the first one in which the application of laponite was actually applied into a sand to evaluate its seismic performance to resist liquefaction. We provided evidence of the ability to engineer and manipulate the granular response of the soil, right? We have a clean sand, and with the proper manipulation of laponite, we can somehow cast the behavior of the sand. And this is probably the most beautiful, right? Because it can has an extension to another fields in geotechnical engineering, which is that we demonstrated the link between the microfabric and the macro response of the soil, meaning the large strain phenomena that you observe in geotechnical engineering, something has to do with what happens with that soil at very, very small strains. The contributions of this work also demonstrated how very small percentages of superplastic fines, remember, laponite has 1000% of plasticity index at least, right? We showed unusual effects of fines on the shear modulus. Usually you observe that when you have fines, the shear modulus is reduced. Here, when we have only 1% of laponite, the shear modulus increases, somehow stiffening the particle contact. We highlighted how different mechanisms are responsible for reduced particle mobility. We provided additional mechanisms to restrict particle mobility. We described the role of interparticle forces, adhesion, and particle bridging on soil behavior, and we set the foundations for using laponite in earthquake engineering. And we are applying these days laponite to tailings because we want to see if we can improve the stability of tailings with laponite. What is our current work? We are applying this into tailings, right? Tailings are not clean sand. Tailings have fines. Here in Chile, particularly in Chile, by law, tailings must have no more than 20% of fines. The monotonic response of sand with laponite, we are studying that too. We are testing with different laponite size fractions. We deliver laponite into sand in suspension form. We are starting to work on that. This is another one very interesting. What is the interaction at the micro scale between sand and Laponite? We already had some testing, but we are trying to get deeper into the two particles, right? And also we have the fines, the non-plastic fines from the silt, in particular from tailings, right? So we are studying tailings, we are studying Ottawa sand, we are studying Laponite, right? So to understand what's going on at the microscale level of particles. And we are studying also we are studying the behavior of bulk Laponite powder. What's going on with this particular material that we receive as a powder that is able to mitigate liquefaction? Acknowledgements, always grateful to my professors at Purdue University, Dr. Santagata and Dr. Bobet, Dr. Drenevich, a very influential professor in my academic career, of course, the Civil Engineering Department of University of Chile, of course, and the National Science Foundations of the USA. Okay, so with that, I have finished my presentation. Thank you very much. It's been a pleasure to be here sharing what we have been doing and what we are doing here in Chile also with tailings. Probably in a couple of months, we are going to have very interesting results for you to show on the outcomes that we have gotten by applying Laponite into tailings. I'm not sure how much it took, but I apologize if I went a little bit over the time limit. Thank you very much for the opportunity of being here. Thank you.
Thank you very much, sir, for giving an insight of the issue. And I was really amazed to see the points you have addressed so well in your